Hi, everybody. It's Professor Mitchell, continuing with Chapter 4. Today we're talking about Section 4.3, which is complements and conditional probability. And part of conditional probability, well, sort of related, is something called Bayes' theorem. We're going to do a very sort of simple form of Bayes' theorem. There is a formula that's attached to Bayes' theorem. It is a kind of scary-looking formula. You might see it if you take a class like finite math, for any of you who might be business majors. Even when I teach finite math, I don't use the formula. I just think there's a simpler way to do it. Anyway, okay, so the concept behind this section, we're going to talk a little more about the concept of at least one. At least one sets off alarm bells for complement rule. And then we talk about conditional probability. So we've sort of talked about conditional probability a little bit already when we talked about the multiplication rule. Okay, when you do the probability that A happens on the first trial and B happens on the second trial, you do probability A happens on the first trial, and then you multiply that by the probability B happens on the second trial, given that A happened on the first trial. That's an example of a conditional probability. And then we're going to do a little brief Bayes' theorem, introduction to Bayes' theorem. Okay, so when you're finding the probability of some event occurring at least once, here are some good things to think about. At least one has the same meaning as one or more. One or more, right? So the only way that one or more doesn't happen is if you get no occurrences of that event, right? The only outcome that's not included in one or more is zero, right? So the moral of the story is that when you're asked about the probability that something happens at least once, it is almost always easier to find the probability that the thing doesn't happen at all and then subtract that from 1 using the complement rule. Okay. All right, so let's go with that. Finding the probability of getting at least one of some event. So start by saying A is the event getting at least one, which means that A complement is the event getting none of that, none of those outcomes. I kind of wish they didn't use the word event here and here. I would prefer outcome. Anyway. Okay. So A is the event getting at least one outcome. I'm going to go with that. A complement means you get none of that outcome. All right, so then we're going to find the probability that event A does not occur, which means the probability that you get none of that particular outcome, and then subtract that answer from 1. So this is going to give you the probability that that outcome occurs at least once. Oops. Okay, so here's an example of using this at least one concept. A study by Square Trade, which is like a cell phone warranty company, right? Found that 6% of damaged iPads were damaged by bags or backpacks. Okay, dropped my backpack, broke my iPad. If 20 damaged iPads are randomly selected, find the probability of getting at least one that was damaged in a bag or backpack. And then they have one of these questions: is the probability high enough so that we can be reasonably sure of getting at least one iPad damaged in a bag or backpack? Okay, so I'm going to start by calling event A the event that we're trying to find the probability of, right? The event at least one of the 20 damaged iPads was damaged in a bag or backpack. That's event A, which means A complement is the event not getting at least one iPad that was damaged in a bag or backpack. And that means that none of the damaged iPads were damaged in a bag or backpack, right? None of them were. So another way of saying that is that all 20 were damaged some other way. None of them was damaged in a bag or backpack. Okay, step 3, find the probability of a complement. So the probability that all 20 were damaged some other way. Well, since 6% of these things were damaged in a bag or backpack, that means that 94% of them were damaged some other way. So if I pick one, the probability it was damaged some other way is 0.94. And when I pick the second one, the probability it was damaged some other way is 0.94. And when I pick the third one, it's 0.94. And when I pick the fourth one, it's 0.94, all the way down to the 20th one. Okay. So the probability that all 20 were damaged some other way, you multiply 0.94 by itself 20 times. Good thing we have exponents. All right. This is going to be 0.94 to the power 20. I would encourage you to try that on your calculator. So you should have a button, an exponent button, that looks either like this with a little caret on it, or some calculators have something that says like x to the y or y to the x. Okay, those are used for doing exponents. So if you do 0.94 to the power 20, you should be able to see how they got this answer, 0.290. Okay. So that is the probability that all 20 were damaged some other way. We want the probability at least one was damaged in a bag or backpack. So remember, that was the original event. It's the complement of what we just found. So to find that probability, you take the 0.290 that we just found, you subtract it from 1, and you find the probability that at least one of these things was damaged in a bag or backpack is 0.710. All right, so for a group of 20 damaged iPads, there is a 0.71 probability of getting at least one that was damaged in a bag or backpack. That probability is kind of high, but I mean, I would not bet very much money that that's going to happen. So to be reasonably sure of getting at least one that was damaged in a bag or backpack, you should pick more than 20. If you upped your sample size to 30 or 40, that would help. It would make this probability go up. Rule of thumb, in case you ever get this question again, I believe your book's working definition of reasonably sure is 95% chance. Probability is at least 0.95. Okay, so now we have conditional probability. Conditional probability of an event is a probability obtained with the additional information that some other event has already occurred. And again, we've kind of seen this a little bit with that multiplication rule. When you use the multiplication rule for dependent events, like if you're sampling without replacement, when you go to pick that second thing, you have to use the additional information about what happened with your first pick. Okay? So that would be an example of a conditional probability. Okay? But now I think we need a formula for it. Okay, so this is the notation that we use for conditional probability. And this is read the probability of B given A. The probability of B given A. That denotes the conditional probability of event B occurring, given that event A has already occurred. There are two ways to find a conditional probability. The first one is called the intuitive approach. So the idea behind the intuitive approach is that if you're trying to find the probability of B, given that A has already occurred, this additional information that A has already occurred sort of reduces your sample space. And I'm going to show you an example of that. So if you can reduce your sample space, get rid of a whole bunch of outcomes that don't fit, then that makes it a really easy way to do this. Okay? So that's called the intuitive approach. The second way is to use a formula. Okay? So here is the formula for the probability of B given A. You find the probability that A and B both occur, and you divide that by the probability that A occurs. All right, so here's an example of finding conditional probability. We have a group of people, and each of these people either uses drugs or doesn't use drugs. I give all those people a drug test, and the test either comes out positive or comes out negative. Okay. All right, so here are the results. 45 drug users tested positive. 5 people who use drugs tested negative. Okay. And then out of the people who don't use drugs, 480 of them tested negative, like they should have. And 25 actually tested positive. So that's called a false positive. Okay. So what they want me to do is if one of these 555 people is randomly selected, find the probability that the subject had a positive test result given that the subject actually uses drugs. Okay. So in the language of conditional probability, using the notation, that looks like that. The probability of getting a positive result given that the subject uses drugs. And then the second question is going to be, if one of the 555 subjects is randomly selected, find the probability that the subject actually uses drugs given that he or she had a positive test result. So it's sort of the reverse of letter A, right? Letter A was find the probability of getting a positive result given that the person uses drugs. And now what's the probability the person uses drugs given that they had a positive result? Okay, so we're starting with the first question. What is the probability that the person tests positive given that the person uses drugs? Okay. So this will make a little more sense, I think, if I go back to the table. Okay. So the idea behind the intuitive approach is reducing your sample space. So let me just bring my pen up here. Okay. So we know that the person uses drugs. Okay. So let's just reduce our sample space down to the people who use drugs, which are these people right here. Okay. These are the people that use drugs. Okay. So what is the probability that a person picked out of only these 50 people uses drugs? Well, that probability is 45 out of 50, isn't it? So again, it's out of 50 because we know that the person uses drugs. We have that extra piece of information. Okay, so we don't have to take it out of 555 people. Okay, so hopefully by looking at the table just now, it makes sense that that this is 45 out of 50. There were 50 drug users. Out of those 50 drug users, 45 had a positive test result. Okay. So the probability of getting a positive test result given that the person uses drugs is 0.9, and they're writing it as 0.900 because they like to write their answers with 3 significant digits, right? Okay. Now we'll look at it using the formula. Okay. So the same result can be found by using the formula. So we'll call event B getting a positive test result. We'll call event A subject uses drugs. So using the formula, which is probability A and B both happen divided by probability of A. Okay. So A and B means the person uses drugs and had a positive result. So if you look back at the table, and I think I'll try this maybe without bringing up the table, there were 45 people that fit that category. Okay. So now this probability of A and B, this is the probability of you pick a random person out of the whole study. What is the probability that that person does drugs and tested positive? That probability is 45 out of 555. Okay. Now the probability on the bottom, that's the probability that the person uses drugs. There were 50 drug users, right? 45 of them tested positive, 5 tested negative. So this probability is going to be 50 out of 555. Okay. All right, so the probability of getting a positive test result given that the subject uses drugs, actually I think I'm going to point to what's written behind me. The probability of B given A, according to the formula, is probability of A and B divided by probability of A. We just figured out probability of A and B is 45 over 555. Probability of A is 50 over 555. So now to simplify that fraction, I'm going to multiply the top and the bottom by 555. That's going to cancel this out, and this is going to cancel this out, and it's going to leave me with 45 over 50. And I'm going to change that into a decimal again. As a decimal, that becomes 0.900. All right, well, I think you're ready to try letter B. So remember, letter B is the probability that the subject uses drugs given that they had a positive test result. Okay, so if you're watching the video, I'm going to ask you to pause the video and try that. And we'll compare notes whenever you're ready. Okay. So we're looking for the probability that the subject uses drugs given that they had a positive test result. So we're going to reduce our sample space down to people who have positive test results, which are these people, right? So you see the difference with letter A? Letter A, we were looking at these 50 people in the top row. Now we're looking at these 70 people in the left column, okay? So out of the 70 people who tested positive, 45 of them actually use drugs. Okay, so among those 70 subjects, 45 use drugs, which means the probability that the person uses drugs given that they tested positive is 45 out of 70. Which is, I think, approximately 0.643. I don't think it's exactly equal. That should be approximately equals. Okay. All right, so probability positive given person uses drugs was 0.9. Probability the person uses drugs given they tested positive is only 0.643. Hopefully this particular drug test is not going to keep somebody from getting a job, all right? Because it's not a very good test, all right? They would definitely want to give this test again, okay? Notice that the two answers are not the same. And that brings us to our final point for this particular video. This is going to be part 1 of section 4.3, okay? Your book calls this confusion of the inverse. I've never run into that term anywhere else. So in this example, we saw that the probability of getting a positive result given that the person uses drugs is not equal to the probability that they use drugs given that they had a positive result. So that's an example of probability B given A is generally not the same thing as probability A given B. They could be equal, but usually they're not. Okay, they call that confusion of the inverse. So here's another good example to illustrate confusion of the inverse. Suppose these events are D, it is dark outside, and M, it is midnight. The probability of D given M, the probability that it's dark given that it's midnight, well, at least in this part of the country, it's always dark at midnight, right? So that probability would be 1. I like how they put this disclaimer in here. We conveniently ignore the Alaskan winter and other such anomalies, right? So at least if you're in California, like we are, the probability that it's dark given that it's midnight is 1, okay? However, the probability that it's midnight given that it's dark, they're saying that that probability is 0, and they're being really technical about this, because if you calculate the time down to like the millionth of a second, the chance that it's exactly midnight is very, very small, all right? Even if you're not that technical about it, if you say, okay, we'll ignore the seconds and just go with, you know, any time between 12 o'clock and 12:01 is midnight, that probability would still be very, very small. Okay? So clearly the probability of D given M is not equal to the probability of M given D. One of those events is certain and the other one is almost impossible.